let's see. All right, started. All right, we'll get rolling. So welcome to the monthly meeting for Modern Dev Charlotte. We have actually a exciting topic today, Cryptography 101. So I know I'm looking forward to learning a lot about what we've got going on. Definitely appreciate those of you who are here attending our meeting and actually attending online and meeting up with us and learning about tech and kind of I guess basically getting some new tools in our tool belt so we can be better software engineers. So without further ado, we'll go ahead and get started with the agenda. So we'll turn it over to Tech Systems and they will share with us what they're doing in the community in Charlotte.
Hey guys, thanks for having me per the usual. Like Richard mentioned, my name's Jenny Guffey. I'm a recruiter with Tech Systems. I focus specifically within our software engineering program. So working with developers like yourselves, just keeping you educated on what the market looks like, especially right now with the uncertainty of the pandemic and going into the last quarter of the year. Happy to have a conversation with anybody who's curious about what the job market looks like. I'll leave my information in the chat below, so feel free to connect with me on LinkedIn or message me on email. I'm happy to help in any way I can.
Awesome. All right, so we'll go ahead and get started and kind of jump right into the technical content. So we have a real treat tonight. We have Robert, who is a very well-known tech community individual. He currently works for Schwan Home Delivery, and he's a Microsoft MVP. He's a Progress developer expert, a ASPInsider, Pluralsight author, and also a third-degree black belt in Tae Kwon Do. So I guess we don't want to upset him in the back alley somewhere.
At least it's virtual today, right?
Yeah, exactly. So at any rate, we'll go ahead and jump right into it. So Robert, take it away.
All right, let me share my screen here. Let me know if you see it okay. That look good?
Yep, great.
Yeah, looking good here.
All right, well, we'll start out. We're going to do Cryptography 101. The good news is this applies to virtually any framework technology that you might use. I happen to be a .NET developer, so I'm going to show the examples in .NET Core with C#. But again, it's the concepts that I'm concerned that you follow. They map pretty well across all of the different frameworks. That's my Twitter. I also have on the bottom here, I've got my Twitter, my email, and blog information. So if you do have questions afterwards, feel free to reach out to me on any of those channels. I am giving you the code. So I've got .NET Core 3.5.1, I think is what I have. And I've got full .NET Framework 4.8. The code is very similar. I'll talk about a few differences. I don't want to spend time doing both because I gave you the code examples. You should be able to follow virtually the same. So again, concepts are more important, but we'll focus on core today. A little bit of background. So cryptography is the science of keeping messages secure. And there's really four main areas we're going to focus on for why cryptography. I think when most people think of cryptography, they think of the first one, which is confidentiality, which is basically I want to obscure the data and protect it from being read. So if you talk to normal people on the street, normal developers who haven't had a lot of experience with it, and you talk about cryptography, they're going to think about confidentiality. We're also going to show how it's used for integrity. So we want to verify that data has not been modified. We also use it a lot for authentication. We want to be able to identify and validate who a user is. And lastly, we're going to use it for non-repudiation, which just means a sender cannot deny later that they sent a message. So that'll cover things like digital signatures. Again, in .NET Core and .NET Full Framework, it's in the system.security.cryptography namespace. That's where you're going to find all the classes that we talk about. Some considerations. When you think about cryptography, again, start with what is your goal? We're going to talk throughout various techniques. I'm going to map those back to these four goals we talked about. You also need to think about how much is your data worth? How long does it need to be secured? Is it something that needs to be secure only for a few seconds? Or is it something that you want to store data in rest that might be around for years or decades? You need to think about your primary threats. Obviously, I'm a web developer, so in transit is one of the primary threats. So between a browser going over the general internet, reaching my web server, I'm concerned about. I'm worried about if people could access my config files. So I'm not going to store secrets in there. I'm going to for the demo, and I'll talk about that because I want to be able to give you the files to use. Could they dump out memory? So I guess in general, I'll tell you my stance. I work for full-time for an e-commerce site. I have to treat my front-end web servers like they're compromisable. In other words, there could be a zero-day attack against IIS in my case, or ASP.NET, that suddenly they could gain full access to my web server because I have a firewall, I have a WAF, I've got my own policies, I've got code to deal with security risks, but there's always a chance there'll be a 0 day, somebody could basically own my web server. So I need to worry about they could potentially take a dump of memory, right? They could do a process dump, which would have all of the stuff that was currently stored in my session variables, any of my variables, could be part of that file that somebody could comb through looking for passwords, credit card numbers, etc. They could modify my pages. So assuming they got admin access to the machine, they could actually change my source code on the server. They could reverse engineer my assemblies. That's not hard to do if you've done that in .NET before. My C# is compiled down to intermediate language. I can just use ILDASM, take any assembly for .NET, reverse engineer it, and if there's secrets in there stored in strings and such, I would be able to see them. So it's just important when you think about your system to think like an attacker would and be able to identify areas that are at risk and being able to understand then how you could mitigate those risks. I need to worry about company security policies. I'm sure you do as well. There's also regulatory compliance. So we take credit cards on our website. So we have to comply with PCI. So there's a lot of rules that come along with that and how you would use cryptography. You also want layered defenses. It's up to you to decide how much is enough based on everything that you saw above, how paranoid you want to be about what somebody could do to your machines. Obviously, the only safe machine, right, is powered off and in a lead box in the corner, right? But that's not going to be useful. We need to manage the risks trading off what could occur as far as a threat with the business value and everything else. And so it's often valuable to have multiple defenses in case they get through one. Lastly, if you don't take anything else away from this talk, don't try to write your own cryptography. So it's not odd when you're with developers that somebody will someday mention and say, why are we using off-the-shelf cryptography? I could write something that nobody would know. It's a secret algorithm. I'm sure it'll be great. Don't try to do that. I mean, it's very unlikely. I've done a lot with cryptography. There's a lot of mathematics to it. You might happen to be somebody that's really interested in that. If you're going to do that, I would go into the channels where you could be a cryptographer and have other people review your stuff. Most of us are not going to be a professional cryptographer, so don't try to write your own. Having it be secret in your mind is not worth all the risks because there's a lot of nuances to the implementations. You want to get your framework and trusted libraries that people have looked at. That's what you want to use for cryptography.
Robert, so
yes.
So there are questions now. There's some questions from Mike in the chat, and
sure.
Like first question I should ask you is, how do you want to handle questions? Do you want just as they come up?
Yeah, this is fine. Yeah,
okay.
I'd rather just take them as we go. And then if my only caveat will be if something gets super detailed because this is a 101, I may pause to the end, or I may take it offline if it's really detailed to get information back to you. But yeah, I don't mind just taking it as we go.
So Mike has a question. Are you going to mention rowhammer and speculative execution or power attacks? And further, like hardware security modules to mitigate them, power and spec X attacks?
I'm not going to get to that level of detail for those in this, no. So did
All
you
right,
have?
I think that's good enough. And
That'll
Mike, you know,
cover-
just
okay.
go ahead and follow up in the
Okay.
chat, right? So Mike says, yeah, no problem. So
Okay. I want to mention this again. It's a 101, but I think this was not easy to find years ago, and it's changed. So I just wanted to mention this as we look at classes in .NET. So they have suffixes on them for cryptography. You'll see things like AES is one of the algorithms we're going to talk about. The class for that is, it could be AES managed. It means something different in the full framework world than it does in .NET Core. So in the past, and you can go to this article and read what each of these means, but if it were managed, that meant that the code was all written in C#. If it ended in CNG, that meant it was a wrapper for cryptography next generation, which is built into various flavors of Windows. If it ended with crypto service provider, that was the old crypto API in older versions of Windows. So it just paid to understand in the past, what are my rules? Do I have to be FIPS compliant? There were other things that played into which one of these suffixes you would want to pick for the class that you wanted to use. It turns out in .NET Core, they've wrapped all of these same classes, all just point to underlying OS libraries. So since .NET Core runs on Windows, Mac, Linux, they took each of these classes, regardless of what the suffix is, they actually implemented it wrapping built-in OS libraries specific to the OS that you're using. I also put in a link here because it's the only part I didn't understand. If you had all these algorithms written, managed, all in C#, that should have been something that could be portable. In other words, in core, you could have just ensured that these classes ran on all three platforms. So why you would wrap it into OS libraries when it was managed, I don't understand, because if you go out to this link, there are some specific classes that don't work on, say, a Mac. So it's important if you're working on .NET Core and you're doing cross-platform, make sure once you pick a class or an algorithm that you come out to this link and make sure it's going to work in your particular deployment environment, because it's wrapping OS libraries. Some of those libraries don't exist, if that makes sense. So I don't want to spend a lot more time on that. I just wanted you to be aware of what these are. I'm going to show you examples in .NET Core that aren't using the suffixes in general. They're just using normal classes. But I just wanted you to be aware of this if you're looking through older code, what those things mean. So we're going to start with hash functions. So the idea with a hash function, they call them a one-way function. It's easy to compute in one direction. So I've got a string here on the left-hand side. If I compute a hash, it's going to come up with this value. It's really easy to compute this way. I used to say it's impossible. I hate to say impossible. Depends on the algorithms, but it should be very hard, nearly impossible to reverse a hash. So the concept is it's easy to go one way. Given a hash, they should not be able to take it back and determine what the string was. So what the hash function will do, no matter how big this is on the left-hand side, when I compute a hash, it's going to be a fixed length representation of what I have on the left-hand side. People often refer to this as a data fingerprint or a digest. We're going to see how you can use hash functions really for two different things, integrity and authentication. Okay, so we'll talk later about encryption. That's the only other thing I like to mention. Hashing is not encryption. Hashing is its own thing. So we're going to go through this example first. In .NET, we talked about system security cryptography. It's got the abstract base class of a hash algorithm, and then it's got specific implementations. I just want to explain some of these because you've probably heard of them before. There is an MD5 class. This is considered broken at this point. You should not be using MD5 for anything anymore. Effectively, it's got flaws in the way it was designed, and with current computing power, it's considered something that you should absolutely not be using. So if you're using it, certainly don't do anything new with it, and you should be moving away from it. The same is true under the SHA family, secure hash algorithms. SHA-1 is now considered broken. And so that is also not something that you should be using. It's very prevalent today. PCI compliance, either last year or the year before, actually said that you're supposed to remove all of this. And so if you're using SHA-1, be aware that that should not be used anymore either. So that leaves us in .NET with SHA-2. So SHA-2 has a number of different hashes, and these are just based on the actual size of the hash. So if you see SHA-256, when you create it, creates a 256-bit hash value, or 384 or 512. There is actually a SHA-3. So NIST, which is one of the standard, I guess you call it organizations or committees, was looking for creating a new hash algorithm. They wanted to make sure that they're telling you now it's safe to use SHA-2, but they wanted to get a head start in case SHA-2 was somehow compromised or broken. They wanted to have something ready, so they had a competition. And so SHA-3, they actually ran the competition. They chose their algorithms. Presently, that's not built into .NET. So there's not a .NET implementation of SHA-3. That's why I don't list it here. Again, you have company policies you have to comply with. In my company, we generally don't want to use third-party security libraries. We would like to use what's built into .NET. And since SHA-2 is still considered not compromised, I use SHA-2. I guess it's up to you whether you'd want to go off of what .NET would provide you and find a third-party library. You just have issues about can you trust that implementation, et cetera. I like to use what's open sourced in .NET and been vetted and used by lots of other people. So that's why I don't show it here. Besides normal hash algorithms, there's also keyed hash algorithms. We'll show you why that matters. So we'll talk about some of those in some of the demos. And there's a lot of other ones. At this point, stick with the SHA-2, and I use SHA-2 512 are the demos I'm going to show you today. Let me go to an example here. Make sure I have my web server running. So I just have a kick off my web server. And looks like I already have it running there. Sorry. Let's look at what hashing would look like. So I've just got a Razor Pages implementation here. And I'm not going to spend a lot of time on the Razor Pages. I'll show you what the actual code will look like or how it will run. So you can just see here's my text, and with SHA-512, that string hashes to that value. So we'll look at how the code does that. So that's in my index CSHTML. So we can see here's the plain text string. Again, I'm using SHA-512. So you can see there in .NET Core, I can just use the generic class. We talked about the managed and the other suffixes. I'm not using those. I'm just using the straight up class .create. And then I'm going to compute the hash. So a couple things I'll note in here because we're going to see it throughout the rest of the talk. Cryptography works on byte arrays, not on strings. So the first task I have to do is I have a normal string here in .NET. I need to convert that into a byte array. So there's lots of different ways to do encoding. I'm going to show you here, I'm using UTF-8. That's a pretty popular encoding. There's UTF-16. In the case of what I'm showing you, and some of the demos I'm doing, it really doesn't matter what I pick, but it really matters if you work with partners and you talk about cryptography, especially if you're encrypting stuff and sharing it with them. These are some of the things you have to agree upon. How am I taking a string and putting it into a byte array? What's the right encoding? So this line just says take my string and get the bytes for it. So now I have a byte array, and then I can just call compute hash on that, and I get back a byte array on the left-hand side. So a byte array is how it's computed. Again, I'm not able to show raw bytes on my web page, so I need to do some kind of conversion to pull it back out of a byte array and put it into a string. So in this case, there's a class called bitConverter that will take that byte array and it'll do this. It'll take each byte and show it as its hex representation with dashes in it. So I just use that. I convert the byte array to a string, and then I just chose for mine to take all the dashes out. So you'll see what you saw here, right? That's the computed hash. If I were to go back into the code, you can see I have an example of another plain text here. If I were to uncomment that and run the same thing, it'll turn out the hash value will be completely different, but it's going to be the same size. So it doesn't matter how big your input is, the size of your hash is dependent on which algorithm you picked. So I picked SHA-512, so that's what that will always turn out to be, that same fixed size. Okay. So that is hashing. And so we'll start talking about some practical ways that we can take advantage of hashing.
One thing, Mike
Sure.
had a comment that, please mention, now it just scrolled down on me. Please mention, several hash functions have been broken, and that includes MD5 and SHA-1 are considered broken. And I think you kind of did reference that, right?
Yeah, that's what I had on the PowerPoint, where I had them struck through because those are considered broken and compromised at the moment.
And he says, even if it's broken, it may still be useful for CRC type function, just not for signing. And SHA, so that's another comment. And SHA and MD5 are still used together for forensics to log data from security logs in courts of law. Then there's the question. Are you going to mention public key coding standards, PKCS, for package formats?
I am going to get into, so nothing for packaging as far as like assemblies or digital signing of assemblies or any of the like the authentic code or any of that kind of stuff I'm not going to get into. I am going to, when we get into encryption, talk about public key cryptography in general. And so we'll get into some of that there, if that makes sense.
Yep. All right. Thanks.
Yep. So again, you can go on the slides. You may be forced to use, like the example was MD5, that could be used for things other than cryptography. So if you're using it for integrity and it doesn't need to be cryptographically secure, generally my recommendation is these things are fast. I mean, SHA-512 is fast and it's secure. I'm just going to use that. There'd be no reason for me to use SHA-1 or MD5 today because they've got these issues as far as being compromised. So back to tamper-proofing. You've probably been to websites where the URL you notice has like customer number equals 101, right? And you can go up there and change it to 102, right? We all work with databases. We know a lot of IDs are sequential. If I went on the URL and typed 102, I might be able to see customer data for a completely different customer. So the idea with tamper-proof query strings is I'm going to use hashing to make it so you can't tamper with the query string. So I'm going to show you how to do that with a hash-based message authentication code. And so the high-level logic is I'm going to take the query string I want, compute a hash of it. I'm going to tack that hash onto the end of the query string. When it gets to the destination, I'm going to peel off the query string that I received, recompute the hash, compare the two hashes, and make sure they match. So we'll get into the code for that. So again, I'll just show you a quick example for that actually running. So here I've got a page, I've got a link here. You can see I've got a query string, A equals 1, B equals 2, C equals 3. You can also see what looks to be a hash on the end here. So if I were to come up here and say, I really want to see A equals 2, right? If I hit enter, now obviously you won't see this on my production site, right? I'm going to turn off detailed errors. I don't want hackers to see this and give them any hints. But for the demo purposes, I wanted you to see what was wrong. It says the query string hash values don't match, right? If I start thinking about how people will cheat, maybe they'll just say, well, how about if I just delete that whole thing, right? Doesn't work because that wasn't sent. So I can keep playing with it. Again, I want to think about how an attacker might attack me. But let's look at what that code looks like. So here, instead of having, that's the query string I want, I'm just going to call this function compute hash. And if I were to jump in there, just for reusability, the first one I wanted embedded in the page so you could see it, but I wanted to keep using this function throughout the rest of the talk. So it takes in a few parameters. It's still using SHA-512. It's still doing the compute hash like we did before, and I'll get into some of these other parameters. And then I let you choose if you want to get it back as hex or base 64 encoding. So I won't spend a lot of time in there. I'll show you a couple things from that in a minute. But again, I've now accomplished my goal. You can't change this query string without me knowing that you tampered with it on the client. So what I want to do is thinking like an attacker again. In my case, I was using this keyed algorithm, which means, if you think about it, if I'm an attacker and I come back to this page and I notice that I think you're using hashing, there aren't that many hash algorithms, right? I can try to figure out how to cheat. So I'm going to show you why using a key mattered. So let me go back over here. I'm just going to pass in. So instead of using a key as my last parameter there, I'm going to say false. I'm going to stop my web server temporarily. I'm going to rebuild that. So I'm still using a hash, but this time I'm not using a key on the server. So I want to show you what that would mean from an attack perspective. Now, if I came back to the page again, and I'm going to see that same hyperlink, hopefully. Up. Need to restart my web server. So if I click on that again, if I were to try to attack this, what I'm going to do is I'm going to say I can create my own hash. I want to use the value 2 here. So I'm going to write a page called hack tamper proof. And if we look at what that page does, it's going to use the same algorithms, right? I'm just going to write a page that says I'm assuming that you are using SHA-512. I can compute a hash just like you can. So if I go back, I just computed what the right hash would be if the query string value was 2. Now if I go back, I click through, I change this to be the value 2. I paste in the right value. And if all is right in the world, it's not. See if I passed in the right place. Oh, okay, I'll do it here. Sorry, I was changing it on the wrong page. Bear with me a moment. So let's try that again. I'll see if I have to go through all those steps again or if I'll get lucky. So let's go to hack, steal that. Let me go back to my page. And click it. Give this one more try, and then if I'm not getting it, I'll just explain it better. I don't know what I'm not changing right here, so, but the idea is that I can figure out how you're actually going to, here. I can guess your algorithm, and if you weren't using a key, I would be able to create my own hash. So I've added one more layer of defense, right? Don't do this in production. I'm doing this because it's a demo. I'm using a keyed hash algorithm, which means it's still a 512, but it takes not only the data to hash, it also takes this key. So if you think of it from a protection standpoint, now not only do you have to guess I'm using hashing, guess the right algorithm, guess the right encoding, but you also have to somehow break into my web server and be able to steal this key. So we'll talk about key storage later, but this is just meant to be an example of you need to think as an attacker would, and that's why I used a key to protect that tamper proofing rather than just do a normal hash, if that makes sense. So that is tamper-proof query strings. The next one we're going to talk about is password storage. So years ago, I did research on Unix machines. And if you ever worked on Unix years and years ago, and I believe they still store it here, there's what's called etc password file. So they said, let's have a password file. We'll store it on the normal Unix file system. But instead of putting your password in that file, we're going to hash your password and put it in that file, because their logic was, if you can't reverse a hash, it's safe to store the hashed value in that file, because if somebody stole the file, they would not be able to reverse the hash and get your password back out. So we use this for authentication. I'm going to show you progressively the arms race of what they tried on Unix, how people attacked it, how they came back and switched it. We're going to walk through that whole process just so you understand how to use hashing and think through that attack model. So again, they're going to use it for authentication. Hackers that know they want to try to get your password, they're not going to try to reverse the hash that you use. They know that if you're using a good hash algorithm, they won't be able to reverse it. So instead, what they did years ago is on Unix, like I said, anybody who had access to the system could take the password file. They were that confident you couldn't do anything with this hashed password. What they had not considered that attackers would do, they basically took an entire online dictionary and they would pre-compute the hash value of every word in the dictionary. And back then, when I did this research, it was pretty common, if you did this, that about 60 to 80% of all the passwords in that file were actually straight out of the dictionary. So you could write something. I'll show you what the code would look like. So what I've got here, I pulled my password file and I found a hashed password in there. I know that I can't reverse this thing. So I just gave you a simple example. I'm going to guess that maybe it's nothing, it's password, or it's secret. Here's where you'd have a loop that actually went through an entire dictionary. I'm going to pre-compute all of these values, and then I'm going to see if I can actually find that value. So let's go run this. And it turns out that hash value is actually secret. So it turned out that this, when you compute the hash of secret using the right hash algorithm, it's going to turn out looking like that. So again, it's true, you can't reverse a hash function. They just didn't think about how an attacker would do this. So years ago, they didn't just use a dictionary. They had a utility called finger in Unix, where you could basically say finger a given user ID, and it would return a profile. So people would put in there, here's my wife, here's my dog. So they would compute the hashes of all of those, and all of those reversed, and it would just make it even more passwords that they can crack. And if you think back then compared to social media today, I mean, it'd be very easy to follow you and target you and find out everything about you and try all sorts of variations of things that you might not think you've said that people could guess might be your password. Make sense? So that was hash passwords. So what they did is, once they found out this dictionary attack occurred, they said, let's make it stronger by using salted passwords. So the idea with the salted password is, I'm going to create some unique random data, and they called it salt. And for each user, they're going to have this random data and their password. They're going to hash the two of them together and store that in the password file. And by the way, they'd have to store your salt in the password file too, because when you come back, type your password again, they need to use the same salt, okay? So each user would have their own salt value. So what that did was it made it really hard for me as a hacker to try to mount a dictionary attack against all of the passwords, because now I don't have to just compute the hash of every word in the dictionary. I have to compute the hash of every word in the dictionary with each salt that was in the password file. So it just made it computationally more difficult for them to attack. So again, they were pretty happy with themselves. I'll show you what that code would look like briefly. So I'm using this generate salt, and I've actually got, I'm using a cryptographically strong. So if you know things about random data on computers is really not that random, right? I mean, if you're not using what they call a cryptographically strong random number generator, it's not considered random enough to actually work for cryptography purposes. So we're going to use this. If you're familiar with Cloudflare, so Cloudflare is a huge internet provider, CDN, reverse proxy vendor. They actually have a whole wall, I think it's in California, of lava lamps. And all of these lava lamps are just doing their thing. They actually use those lava lamps for entropy to help create random data. So they're pulling in things that are truly random from outside a computer to get even better random numbers. But the best that we can hope for, use this random number generator in .NET. So I've got some salt. The computing the hash is basically the same. I'm going to pass in the password and also the salt. So if we go back and look at what happens inside this function, it's really whatever I was doing before. I'm just concatenating the data with that salt value. Okay. So what that did is it did make it hard for me to tack the entire password file. But because you stored the salt and you still left the password file as a clearly readable text file, I would look for the user that was named admin, and I would take their salt and take the dictionary and hope that they chose a bad password, because if I can get in as the admin user, I can basically get in as anybody. Again, they did one more step. I'll just mention it here. Again, they said, well, let's make it a little harder yet again. If I were to store this thing here, I can get another set of random data. This I'm not going to put in the password file. I'm going to use the same one for everybody. Think of it as a sort of a random key. If I also use this, I've done one more layer of defense again, right? Now, not only do you have to have my salt, you have to be able to do the hash, you're going to have to be able to compromise my web server and get my secret. Again, don't embed it directly in the code. We'll talk about that kind of stuff later. But for the demo purposes, it's just made it that much more difficult for somebody to attack me. So password systems started doing all of that and then some to try to protect their passwords. Today, what people do instead, I'm going to give you this example, PBK DF2. The more popular non.NET implementation is bcrypt is another algorithm that's used by a lot of people for password hashing. The conceptual is the same. As computers get faster, computing a SHA-512 hash is super fast these days, and people actually make specialized hardware to be able to do fast hashing. The idea with these functions, the bcrypts, the PBK DF2s, they add what's called a work factor. So they basically make it intentionally slow to compute a hash. So they use what's called a work factor, and basically I'm choosing how many iterations I want to run of this function while I compute the hash. And I need to pick something that's slow enough that will make it hard for an attacker. So if they tried to do a dictionary and they wanted to hash the entire dictionary, if I purposely made this thing take about, say, a second, now it's going to take a second per word in the dictionary. It just makes it harder for them to attack me. I have to choose a value that's a good trade-off, though, because if I use this for password stuff, when you come back and type your password to log in, I need to do the same function. I don't want to make that be 10 seconds because I don't want you to wait that long. So you got to figure out what's a good trade-off. But I will show you how that works. So again, conceptually, think bcrypt. These are all the same kind of categories. Again, I'm more concerned about the thought process here. I've got the hash. I set the number of iterations. So if I were to go run this, oops, sorry, I will compute the, so as I run it, I chose a number of iterations that was still relatively fast. I can go tweak that, and if I were to change this, add a couple more zeros, it's just going to make it that much more time consuming to compute the hashes. So if you talk about modern hashing for password protection, they use algorithms like this and do that trade-off so that it makes it hard for an attacker to pre-compute a bunch of hash values, if that makes sense. So I'll pause there quick. That's hashing. We talked about using it for integrity to make sure things haven't been modified. We talked about using it for authentication. So I'm going to leave hashing now and step into encryption. So let's look at what this would look like. A lot of terminology. So these are just common terms you'll see everywhere when it comes to cryptography. So plain text is my original data. Encryption is the process of obscuring that data. Ciphertext is the encrypted data, and then I'm going to use decryption as the process to recover the original plain text. The cipher is the algorithm I'm going to use for performing the encryption and decryption, and I'm going to use this for confidentiality. So this is probably the most popular one, but when people think about encryption again, they generally think of this diagram and symmetric algorithms. I have my plain text. I'm going to encrypt and get ciphertext. I'm going to decrypt and get back. And both of these operations use the same secret key. That's why they call it symmetric. It's the same key for encryption and decryption. If you use a good algorithm, the primary attack against this is brute force. In other words, they can't break the algorithm. So they have to basically try every possible key in the key space. And so that's generally how they're going to attack it. This thing is great, it's super fast. The main problem with it is the key distribution is difficult, right? If I met one of you today in the talk and said, let's start exchanging some secrets here, I'm stuck with how do I get you the secret key? Well, I'm kind of back at the same problem we started with, right? I have a secret I want to share with you, but I can't unless it's encrypted. Well, I can't encrypt it till we agree on the secret key. So although they're fast, that's going to be the issue we're going to focus on. There's a number of different algorithms built into .NET. I'm going to talk about Raindoll, which is a version of AES. DES has been considered compromised for a long time. There's also triple DES. AES is actually the US government standard for encryption, and it's very popular. So that's the one that I'm going to focus on for this talk. And again, there's a whole host of other algorithms outside of .NET as well, if you're interested in some of those. The .NET symmetric algorithm we're going to go through is called a block cipher, which just means it's going to take the data you want to encrypt and it's going to break it into blocks based on the block size. So that's why they call it a block cipher. If you think, if I have a message and I've got 128 bits for a block size or 256, eventually the very last part of my message isn't going to magically fit in whatever that block is. So I've got to do what's called padding. So I listed a couple different ways that you can do padding. I'm going to focus on why zeros is bad and why I recommend this approach for padding. I'm also going to talk about there's various modes. There's a lot more modes than this as well. Again, since it's a 101 talk, I just want to show you CBC is a pretty popular one. I'm going to compare that against ECB and why you should never use that mode. And lastly, with symmetric algorithms, because they're a block, this CBC mode says, normally I'm going to encrypt the first block, get the ciphertext, then I do the next block and the next block. They realized that that isn't random enough, so they changed the CBC mode, says I'm going to encrypt the first block, but when I encrypt the second block, I'm going to use data from the first block to add some randomness to it, which is great. But then they said, where am I going to get random stuff for the very first block? That's what's called this initialization vector. So again, it's just random data used to seed the first block of encryption. Again, I'm not a cryptographer. Every time I see this, I've read many times this is true. I don't follow the math on why this is this way, but the initialization vector does not need to be a secret. So I'm going to take the plain text, I'm going to get the ciphertext, I'm going to send it to you. You're going to have the same secret key. You need that initialization vector, use the same algorithm, use our shared key. You'll be able to do the decryption. The important part with this initialization vector is you never reuse it. Every time I'm going to send you something, I need to recompute this. So we'll look at an example, and some of this will be more obvious why you need to do it this way. So I'm going to pull up my page just to show you what the user interface would look like. I'm just going to type test, encrypt it. You see, every time I encrypt, I'm getting a new fresh initialization vector. That's my ciphertext. I'm going to give you these two things. You're going to know the secret key, so you're going to be able to decrypt it and get back to the original plain text. So if we look at the code for this, we'll just look at encryption first. I have a function here that creates my cipher. So here I'm using AES, and I listed what the defaults were up here. I'm switching it to use that ISO. All that says for the padding is whatever space is left in the last block, put in random data. And then I need to have a secret key. So again, don't do this in production, but for your demo to be able to give you the code, that is my generated secret key. So I'm going to create that cipher. It's going to automatically make a fresh initialization vector for me. And then this is the code that does the actual encryption. So I'm going to take this string. Again, I'm going to use UTF-8 to get it into a byte array. And then this is the actual encryption line. So I'm saying, please encrypt that plain text. And then in this case, I chose to just use base 64 encoding instead of hex. I could have done whatever I wanted. I used base 64 just to show you that's another choice. And that's what got displayed on the page. If we go back, that's what you see here. That's base 64 encoded. You can tell because it's going to end with that double equals like that. So the good news is if you look at this, it's really very straightforward and not a lot of code to do proper encryption with a strong algorithm. So now I want to show you why you don't use these other two modes. So let me change these. I'm going to stop my web server. Let me rebuild that. So I switched it to be the padding is all zeros at the end. And this ECB mode just says, don't use an initialization vector. Just basically encrypt each block. So if we go look at what this will do now, I'll go back to symmetric. I'll type test. And the important thing you see every time I'm encrypting, it's giving the exact same value back. And that's bad. I mean, if you follow history, anytime you're attacking cryptography, when things look the same, you start to learn things. And so that's why that mode is horrible. It does do encryption, but if I were watching on the wire and I saw you send messages every day, and maybe there's only 5 or 6 different values you send, I'm going to keep seeing the same stuff all the time. That's why that's a horrible mode, and never use that for AES. You want to stick with the better padding, and you want to use the CBC mode so that you get true randomness incorporated. So even if I had the exact same message every time, the encrypted value would be different because of that initialization vector, if that makes sense. So that is symmetric. So we talked about the problem with it is it's hard to distribute keys. So asymmetric, if you've heard of its other word, is public-private key encryption. I will generate for myself a public-private key pair, and these two are mathematically related to each other. If I have a public key, I can't figure out your private. It turns out if I have my private, I can figure out a public. The good news about these is it gets rid of the key distribution problem. The bad news is it's about 1,000 times slower than symmetric. So there's certain use cases where asymmetric makes sense. Most of the time in the real world, as we'll talk about later, you usually use asymmetric and create a symmetric key that you use to do the real encryption, and you only use asymmetric to get that symmetric key to the other party. So if you think of the diagram here, I'm sending to this receiver, and they are going to give me their public key, Maybe it's part of their email signature, maybe it's on their Twitter, LinkedIn, whatever. I'm going to get their public key. I'm going to take the plain text and encrypt it with their public key. As soon as I do that, the only thing that will decrypt it is the matching private key. So as long as they keep their private key hidden and no one gets access to it, they're the only one who will be able to decrypt, and we haven't had any issue having to distribute keys to each other. Again, there's a lot of different algorithms for this. Probably the most popular is RSA, so I'm going to focus on that one. We'll look at what some of the code looks like for you. So again, I'll just type that. That's what the ciphertext looks like. If I decrypt it, I'm back to the plain text. And if we look at what the code looks like, so you can actually generate RSA keys. So if you look in here, I have a page that will create these public-private keys for you. So I've created those and I put them here in a string. Again, easy for the demo. The encryption, again, is straightforward. I just create a cipher. And that's just RSA. And I tell it to use the key pair that I have above. One odd thing about .NET Core, it used to be able to read these XML strings. And last time I checked, that's still not implemented. So I'm actually using a third-party library to read this. I'm hoping .NET Core will eventually put that back. But again, I take the plain text, UTF-8, encode it. I like the words they use better for this. Use encryption. Here, there's some more padding you need to think about. Don't use PKCS1. You want to use this instead. But again, pretty straightforward. If I have your public key in a string, it's simple for me to encrypt it. And decryption is basically the reverse, right? I'll have the private key, I'll be able to do the decryption. So that is asymmetric. So we'll talk about a practical way to use asymmetric. So if you think about, again, I'm an e-commerce site. I want to take your credit card number. How do I do that securely? If I were to use hashing, it wouldn't work because I can't get your credit card number out later when I need it. So I need to use encryption. If I use symmetric encryption, that means I need to have the secret key stored on my web server. I really don't want to do that because it's compromisable. So instead, what's typical today, you create an RSA key pair. You put the public key on your web server. As soon as you take the credit card number, you encrypt it using that public key. Then your private key is stored internally behind your firewall that nobody can get to. So I can now write the ciphertext out to the database, do whatever I need with it. The internal system that needs to talk to the payment processor has the private key. It can decrypt it, get the credit card back. Everything works great. So I'll show you what that would look like. So I'm going to type in something here. Test 2 we'll try. So this is my web server. It just encrypted it with the public key. If you imagine then I went internal. I'm behind the firewall. I have a process that takes that off the database. I decrypt it because I have the private key, and I'm back where I expected. Most payment processors actually create public-private keys and give you a specific public key to use for encryption. So as soon as you encrypt with their public key, I can store it anywhere I want internally. There's no way my company can even decrypt that. The only person who can decrypt that is the credit card processor. So that's a good technique. Again, gets away from some of the key storage issues. So I'll pause there quick. We're about to go in kind of the big demo of the day. Are there any questions so far on that?
Yeah, well, Mike has a question comment, I guess. So RSA was very popular, but it's been largely supplanted with ECDF, elliptic curve differential Hellmans. I don't know.
It's a mouthful. Yep.
So you know, is that your understanding as well, due to key size reduction with same strength?
Yeah, I guess in real world implementations today, RSA is less used. It's still considered, it's not considered at this point to be compromised, but they are looking at different, especially with dawning of quantum computing and everything else, there are other algorithms that you can take advantage of. You'll typically run into RSA a lot because it's still what a lot of your partners are going to use, but there are other choices today.
I have a question based on like the symmetric section, right? Which is the initialization vector versus the salt. So so those are both very confusing. They're both adding randomization to your encryption. Can you kind of explain the difference there?
Yeah, so the salt is for the hashing, and it needs to be the same value. So when we talked about hashing before, I'm going to take your password and hash it, right? I just didn't want to have it that somebody could easily compute the whole dictionary. I take this random salt. I need to keep that same salt for you every time you come back, because I need to take your password, add the salt to it to be able to do the hash. Then I compare it to the same thing that I have in the password file or the database. So that salt is random, but it has to stay consistent and unique to you, if that makes sense. From a symmetric standpoint, the initialization vector, and I'm going to have to make a better diagram for this. If I had it on the diagram here, there's an IV that comes in here along with your plain text, gets encrypted. And it's also part of the decryption process. That needs to be random and different every single time, because it's just an input. And like I said, I wish I had a better diagram for this. If I do the block size, if you imagine I've got a message and I break it into 256-bit blocks, the IV is random data used to help encrypt the first block, and then it's not used anymore. Then the result of that first block encryption is used to encrypt the second block. So if you looked at this ECB mode, it would just say, I'm going to encrypt the first block and then I'm done. I'm going to encrypt the second block, then I'm done. But that just keeps the same input would end up with the same output. So the initialization vector just adds randomness to that specific encryption and decryption. Does that help?
Gotcha. Yes, okay. That does. And then you mentioned, you know, I am well aware that randomness is very, very important.
Yep.
Could you kind of explain why that is, right? What if it's a pseudo-random generator instead of a fully, you know, hardware security module random?
Yep.
What goes wrong?
So the risk with that is, just like when I did the ECB mode and the same thing I encrypted, if I were able to guess, like let's say you were not using a truly random number generator, and it could only give you random numbers between 1 and 10, right? Then I could easily guess. I would try 10 times and brute force through that because it's not random enough. And a lot of the old systems used system time as its seed. And so I could figure about what time you did something, and I could guess what the seeds would be, and therefore you've lost your randomness, if that makes sense.
Okay, meaning,
so I don't know
if
if
you
I'm
do it at a
explaining
certain
it great.
time of the day, right, attackers would be able to see that, hey, it lines up to like we can see this random part because it's not truly random.
Yeah, so I think of it, I mean, the easy way for me was like the 1 to 10 example versus 1 to 100 million. Your one random might just be cycle you between the numbers 1 and 10. That's really not enough to make it difficult, as opposed to a better one's going to give you a lot more diverse and less obvious based on time and other things. That's why I was alluding to the Cloudflare thing goes outside of computers, because in the end, computers are never truly random, right? I mean, there are a set of rules, and that's why Cloudflare uses those lava lamps, because that's a non-computer thing. How the lava is flowing on those thousands of lamps, somehow they get snapshot of it or whatever they do. That's how they get randomness, because they know it's not based on computers and rules. It's truly an outside the system source of randomness, if that makes sense.
Yeah. Okay. Okay. And then I know there were a couple other questions.
Okay.
So Mike is asking, people have gone to RSA 4096, which is big and slow to maintain security past a given time of usefulness. That's why they're moving away from RSA.
Yep.
And I'm trying to understand this one really quickly. So if you use a new symmetric key every time, as HTTPS does, then ECB is fine. It depends on the protocol. Nobody would always send the same message, hello, every day at the same time with the same symmetric key, just change keys with asymmetric crypto.
Yeah, I guess I mean, for here, again, for the 101, I have some resources at the end. If you follow World War II and the Enigma, the way they broke it with some of their bombs and stuff, what bombs were their computer systems that broke it, the headers and the messages always started with the same stuff. And so that introduced some non-randomness into the cryptography every single day, which ended up making it so they had enough flaws, reduced the key space, et cetera, and they were able to break things. So it's just one of those, again, initialization vectors are needed. You need them to be truly random. Don't ever reuse them. Or, anytime you're giving up some of your randomness, you're basically giving up some of the effectiveness of your cryptography, if that makes sense.
Yep, gotcha. Okay, thanks.
Okay, yep. So this is kind of the big demo that I incorporate everything we've learned so far. So digital signatures are meant to provide integrity and non-repudiation, right? So if I were doing a contract with you online, rather than a physical signature, I need a way to prove two things: that the thing that we signed didn't get tampered with. And I also want it to be that if you signed it, you can't later say it wasn't you. So that's what digital signatures, as far as goals, it wants to do those two things. The way I do a digital signature then, I am going to get your public key. I'm going to do, and so just to make it more difficult, I chose for this demo, by default, digital signatures do not require encryption. Okay. So in other words, if I'm sending you a contract, if I don't care that somebody can read the contract, technically digital signatures don't need me to encrypt it. I chose for this to say what I think is realistic. I want to send you something that I don't want anyone to see, that we are sure hasn't been tampered with, and that you can prove it came from me. Okay. So what I'm going to do with this is, so let's do the conceptual first. I have plain text. I'm going to do the encryption just like I did before. I'm going to take your public key and do the encryption. We already saw that, right? That's just asymmetric. Now I have ciphertext. Now I can compute a hash of the ciphertext and encrypt that ciphertext. So this is the digital signature part. You are effectively taking, in this case, I'm using my own private key to encrypt or sign the hash, and I have a signature. Now I can send you the ciphertext and the signature, and you're going to be able to prove it came from me. So this did the cryptography part, and the only way that I could have signed it is if I had the private key. You're going to use my public key to prove that I'm the one who signed it, because those keys are reverses of each other. So if I signed it with my private key, my public is the only one that can decrypt or prove that it was signed properly. So I'm going to show you this example. So I've got a sender. And again, I'm going to give you the code for this, and we're running a little late, so I won't go through it all in detail. It'll look pretty familiar. I'm going to first get a sender cipher. That's me as the sender. I'm going to get a receiver cipher that has your public key. Here's my secret credit card stuff. I'm going to get the bytes for it. I'm going to do the encryption. So all of this stuff here is the normal encryption you saw before. If I go down here, then I'm going to compute the hash of that ciphertext. And then this is how in .NET I can sign it. So I'm using a SHA-512 hash and RSA signatures. I create the signature, and now I have a digital signature because I did it with my private key. And then I chose to URL encode this with base 64 so I could shove it onto the URL. So if I show you what this looks like, this would be an example if I were sending something to another party. I can send the ciphertext, which is the secret. And then if you go across the URL, I'm going to send you the signature as well. And then when you got it, you would have the right keys to be able to prove that I signed it, and you'd have your own private key so you could decrypt it. Okay. So again, that's kind of detailed. I'll let you look through all the code on that. Again, the good news is, if you think about it, that's really not a lot of code. I mean, for the power you're getting for digital signatures and all the things we just said, nobody could read it. You could make sure it wasn't tampered with, and you could prove that I signed it. That's really not a lot of code. Again, built on trusted .NET implementations. We'll talk about HTTPS because people are really familiar with this. Everybody uses, I hope, this on their website. So when you want to set up HTTPS, you go get a certificate. And really what a certificate is it's a server's public key that is digitally signed by a certificate authority. So there's a number of trusted certificate authorities, like Let's Encrypt, for instance, is one I use that's free. I will get a public-private key pair. I'll prove to them that I am the owner of this key. They will sign it. Browsers have a list of well-known certificate authorities. So when they connect to my web server, the browser will get the server certificate. They'll pull out the public key. They'll be able to verify the digital signature belongs to Let's Encrypt. The browser says Let's Encrypt is trustworthy. So again, the browser gets the server certificate. Once it gets it, the browser validates that the certificate is okay. Then the browser chooses a symmetric key, a random one, and initialization vector. And then they can talk to the server using symmetric because that's so much faster than asymmetric. So it kind of uses both of those to accomplish what we all use every day, which is how we get stuff from a browser to a server on the crazy internet without having stuff be intercepted and be trustworthy in transit. So just kind of a high level of actual uses of stuff. So the worst thing in cryptography is actually storage. So I talk about key sizes. I personally use the highest key sizes I can use. I'm not going to get fired. So I've run tests, and you can do this for yourself. Try AES with 256 versus 128, milliseconds difference at most, and that's when I ran it with a lot of iterations. I'm not going to get fired over being milliseconds slower. I will get fired if somebody breaks into my site and we have a breach because I chose to use a key that was too small. So in general, use the strongest keys that you can. Key storage, way too detailed for a 101. Again, this gets into a lot of the, depends on your environment. Can you put it in Azure Key Vault? Can I store it in web config? So ASP.NET Web Forms had a way to encrypt the app settings section using RSA on the server so that I could have it encrypted in the actual web config file. ASP.NET would decrypt it when it needed it, pulled the key out of there. I kind of avoid this whole thing. So when we talked about keys before, I just don't store symmetric keys on my web servers, right? I avoided that by using asymmetric instead and putting my public key on the web server. That I can technically hard code in a string. It's a public key and I don't have to care. So that's how I get around key storage. I know it's not that simple. There's going to be use cases where you're stuck. And like I said, this is the worst part of cryptography is how do I have a secret on what's a public web server that could get compromised? Where could I put that to give myself some confidence that it won't get stolen, right? So quick summary, again, if you don't take anything from this, don't write your own cryptography, right? Choose trusted algorithms. As we went through the talk, we talked about MD5, some of those you shouldn't use anymore. AES is still considered strong. There's good options within .NET if it turns out that you get to the point where you think a .NET implementation doesn't have what you want. There are a lot of third-party implementations as well. Just make sure you're getting them from trusted sources that are being vetted. And again, use trusted algorithms, implementations. Know why you're using stuff. So a lot of times people are talking about encrypting passwords, for instance. As soon as I do that, instead of using hashing, now I have a key problem because I need to be able to decrypt it on the web server. So in general, use hashing to do integrity or to prove you both know the same thing. Use symmetric when you can because it's fast. but you will have to fall back to asymmetric to get keys exchanged, do digital signatures, etc. Think about your threats. Make sure you choose the proper countermeasures. I've got a couple resources for you. So I do have a Pluralsight course on this, Intro to Cryptography in .NET. So that's .NET full framework. I've also had a couple webcasts that have it online where you can see some of what we saw today. There's some good books on cryptography. So Applied Cryptography is a great book. It's older, gets into all the details. Like I said, I'm not a mathematician. I don't want to go through exactly how AES works and how all the bit shifting works and stuff. I trust others to do that for me. I mean, at my level, I need to have a trusted algorithm I can use. If you're into that stuff, though, all the books in the middle are good details of exactly how algorithms are implemented. If you're interested in more of the history, so if you want to see like Caesar cipher years ago or Cytales or the vignette cipher or how did people break Enigma, all those kind of things, these bottom books are good books that just go through a lot of that history of attackers and protectors, so to speak, the arms race, how they did stuff. Those are kind of cool books to read for that. Again, that's my Twitter, my email, my blog. That's the link that has the slides and the code. So I'll leave that there and just open it back up for any general questions.
Great. Yeah, I know I've heard that applied cryptography before, right? So one thing is is that book recommended for those of us that wish to apply it as a user, right? Like basically like run through framework, run through already created algorithms, or is it a delve deep book?
So these in the middle are delve deep, but I
Okay.
use them all for what you just said. Even though they delve deep, they often still touch on best practice, one layer up, how you should use this stuff. I don't have it listed here yet, and I don't have it sitting next to me right now. I just read Practical Cryptography in Python, and I'm not a Python developer, so I skipped all the code parts of it. But it had very current, and one of the persons was asking a lot of questions. He gets into a lot of specific newer algorithms and more of a how you should use cryptography level, kind of what this talk is hoping. I'm trying to give you a background in cryptography as a 101. Those kind of books, that Practical Cryptography in Python, are the layer. He still gets into a little bit of the math that you can skip, but it's more you should use this mode and here's why, or you should use this algorithm. He talks about why MD5 is actually broken. So it's a lot more at my level than these middle ones are really your cryptography. They're still worth getting, like you hinted at. You still learn things about AES, right? And modes that you might use. You also just have to skip 50 pages of bit shifting diagrams and math. You know what I mean?
Right.
Now, the bad news with that one, it's older too. I mean, I've got a second edition of his, but he hasn't touched it in a while. And so some of the newer concepts, he's got other books that get into newer stuff. But it's a little bit dated. But again, for understanding why you need an initialization vector and that kind of stuff, it's helpful.
Gotcha. Okay. So a couple of things. Yeah. So Paul was asking if you could flip back to that. Yep. And then Mike was mentioning that Schneier is great and Oracle. And yeah, that seems to be the general consensus, right? It's like that's the book to get.
Yes.
That you mentioned, the applied cryptography. And Mike also mentions that the reason he mentioned PKCS is to avoid all of the BER / DER and ASN1 encoding, etc. As you can see, I can't even read it well. I am not familiar myself. I have seen ASN1. And he mentions that Bruce has a newsletter every month.
Yep. And I follow him on Twitter, and he's got interesting things all the time. So, and he also did, I think, Blowfish and Twofish, which were some of the competitive algorithms for what became. So AES was meant to be it was a competition again, and Raindahl won it. Blowfish and Twofish, I think, are both from Schneier and didn't win, but are considered still good algorithms. There are various reasons why it didn't become AES. Yeah, there's a lot of good people to follow in the space. But But again, that book is a great start to. I want to understand how cryptography works in general. Like I said, you can skip over the math stuff if you want, and I would supplement it just with a couple newer books that get more into current algorithms and practical use.
Gotcha. All right. And if anybody else has any questions, please feel free to, unmute your mic or ask in the chat. And the last question I had was just salt. Why is it called salt?
I do not know, to be honest with you.
Like maybe just like salt it with a little randomness.
That would be my guess. I mean, in some of the arms race again too, there's pepper, other things that have come up and been used for various, other ways to add random data. I always used to call what I did entropy, which is really just a word for randomness. I want to see if I have it in that pass. The one this thing. I don't know if that's what people would call pepper. I never found a good term for that. But yeah, how they came up with the word salt, I'm not quite sure. But I actually I did research when I was an undergrad, and the password cracking was part of what I was supposed to do. Unfortunately, I ran it on the wrong system that apparently I wasn't authorized to run it on. So that's a whole different story. But yeah, it's interesting to follow the arms race of what they did, how they circumvented, how they came back, made it stronger. Cryptography can get really detailed, but again, once you find the right algorithms and stuff to use, it's also not hard to use. If I pop into whatever this one is, it's also not hard to use. Get the right algorithms, store your keys well, and it's not a lot of code. So.
Yep, and Mike mentions he thinks it's from salting a mine. I have no familiarity with how they do mining, but yeah, absolutely, it could be. Warfare in ancient times. So Misho thinks maybe warfare in ancient times when people would salt the wells or farmland to make it less hospitable.
Yeah.
I could see that.
Yeah, I could see that. That's a good explanation. It's funny. My daughter did a cryptography talk for kids. And one of the things they did years ago was they would shave people's heads, write the message on, let their hair grow back, send them running across the battlefield, and then shave them, right, and read the message. So I put on a big rainbow wig with a bald wig with a message to help her demonstrate this for the kids. But yeah, not quite timely enough for these days. Wait
right.
a month before your hair grows and hope your message about where the battlefield is still valid. But yeah, some of those history books are cool too. I mean, I like
the Caesar cipher. I understood the Caesar cipher, just instead of A, it's a D, right? Just shift it 3 letters. Like, okay, like that I can grasp. And then it just got so much harder. I don't know.
If you read, some of these are cool because they really take you on a nice progression of substitution ciphers. How did that get broken? Frequency analysis. Then how did that end up being the vignette cipher? I found them interesting. I mean, they just give you some history of even, major events of people losing their life over cryptography that wasn't secure, etc. So some good books there.
Well, Richard, did you have anything else you wanted to add to kind of close out?
I did not, other than thank you, Robert, for the great presentation. We definitely appreciate it. And thank you, everyone, for, virtual clap, right? Thanks, everybody, for spending a little over an hour this evening with us and joining us through this cryptography journey. And we will post the recording hopefully tonight, so you'll have that as a reference, and look forward to next month. We don't have that planned out yet, but we will be making an announcement as soon as we can. Thanks so much, and have a wonderful evening.
Thank you.
Yes. Bye-bye. Hopefully see you guys next month.
See ya.